In the previous video, we calculated what is the value of N0, which is the thermal equilibrium electron concentration and thermal equilibrium hole concentration in the conduction band and valence band respectively. Now the value we found is Nc, effective density of states in the conduction band, then exponential of minus of Ec minus Ef divided by K Boltzmann constant and T the absolute temperature, which can be rearranged like Nc exponential of, rewritten as exponential of minus of, if I'll write this Ec minus EFI, EFI I'm writing for intrinsic Fermi energy level, plus EF minus EFI all divided by KT. So now here if you'll see, this is minus and minus plus EFI, and here you got minus EFI will be cancelled and you will get the original value that was there in the bracket. So we can just simplify this expression writing this way: Nc exponential of, taking this these two terms separately, Ec minus EFI divided by KT, this one term, and then multiplied with exponential of the other term that will remain is EF minus EFI divided by KT. Okay, so this is the term. So now we can write this whole thing, this thing here as Ni, okay, and we can rewrite it as Ni exponential of EF minus EFI divided by KT. So this is my Ni exponential of EF minus EFI by KT. This is the electron concentration in thermal equilibrium in an extrinsic semiconductor, So N0, the same way we can write, we have already derived the thermal equilibrium concentration of holes, can be written as Nv exponential of minus of EF minus EV, the valence band energy, divided by KT, which can further be rewritten as Nv exponential of, in the bracket we can write this, rearrange this as EF minus EFI, where EF is the Fermi energy level of the extrinsic semiconductor, and EFI for the intrinsic semiconductor. When there was no doping, what is the Fermi energy level, that is EFI, and then plus EV minus EFI divided by KT. Okay, so similar way we can just write it, divide it into two terms, Nv exponential of first one EV minus EFI divided by KT, that is the whole concentration in the intrinsic semiconductor, multiplied with this extra term exponential of minus of EF minus EFI, that gives you the relative change in the Fermi energy level after doping. So KT, that is Ni, the intrinsic concentration of holes. This intrinsic concentration of holes and intrinsic concentration of electrons for intrinsic semiconductor is always the same. So Ni exponential of, so substituting for this whole thing as Ni and exponential of, we have this is minus of EF minus EFI divided by KT. This EF and EFI minus EFI, the difference in the Fermi energy level, is a measure of doping, what amount of extra atoms are added to the intrinsic semiconductor, so that there is a relative change in the Fermi energy level from EFI to EF. So that will give you what amount of extra in the whole concentration will be. Okay, here. So now this way we can just write, if I'll write the formula that we got in terms of intrinsic concentration, Ni exponential of EF, the Fermi energy level in the doped semiconductor or extrinsic semiconductor, minus EFI when it was an intrinsic semiconductor, there was no doping, divided by KT, and we got this P0, which is the thermal equilibrium hole concentration in the extrinsic semiconductor, is given by Ni exponential of, we got minus of EF minus EFI, that's the relative change in the Fermi energy level, divided by KT. Right, now if I write EF is greater than EFI, the intrinsic Fermi energy level, the position of the Fermi energy level is above the position of the intrinsic Fermi energy level, then we can write the concentration of electron is greater than the intrinsic concentration. From here it is visible exponential of EF minus EFI. If EF is greater than EFI, definitely this EF minus EFI by KT term will be greater than I mean positive or greater than 1, and hence you will get N0 much greater than, or N0 is greater than Ni, and P0 will be less than Ni. So we can write here concentration of electron will be greater than concentration of hole here in this case. So we will say the semiconductor is N-type. If I will take EF is less than EFI, so the Fermi energy level, new Fermi energy level, is below the intrinsic Fermi energy level, then we can say from the equation above, N0 will be less than Ni and E0 will be greater than Ni. So this will give us that the concentration of hole is greater than concentration of electron, and it gives, or it refers to a p-type semiconductor. Okay, now if we take the product of N0 and P0, N0 P0 product will give us, substitute the value of N0 P0, that is thermal equilibrium, electron concentration and thermal equilibrium hole concentration, substitute the values for them, and see exponential of minus of EC minus EF divided by KT multiplied with, for P0 we have already determined this is NB, effective density of states in the valence band, exponential of minus of EF minus EV divided by KT, Boltzmann constant, T is absolute temperature, that gives us NC NV, exponential of, adding all the terms, we got minus EC plus EF minus EF plus EV divided by KT, that gives NC NV exponential of minus of EC minus EV divided by KT. Okay, that is NC NV exponential of EC minus EV. EC minus EV is the conduction band, this is the valence band. Here we said this is EV, the valence band, and this is EC, the conduction band, and the gap between the energy gap between conduction and valence band is called the band gap, EG, the band gap energy, and hence writing that way, this is minus Eg for the band gap divided by kT. So this is one expression for N0 P0, which is written as N I square of the intrinsic concentration. Product of N0 P0 is always constant for a given semiconductor material at a given temperature. So we got the value of N0 is greater than P0 in N-type semiconductor. In N-type semiconductor, we have the concentration of electron is more than the concentration of hole. And we said the position of the Fermi energy level will be shifted upward and will be above the intrinsic Fermi energy level in N-type semiconductor. In P-type semiconductor, we said the thermal equilibrium hole concentration will be greater than the thermal equilibrium electron concentration for P-type semiconductor, and the position of the Fermi energy level will be shifted downward and will be below the intrinsic Fermi energy level. So if you show the band diagram for the N-type semiconductor, we have this as the valence band and we have the conduction band, and the intrinsic Fermi energy level is somewhere in between EC and EV. So this is the position of the intrinsic Fermi energy level. This is same for the intrinsic semiconductor. Over here we have EV and we have EC and we have the intrinsic Fermi energy level EFI. Now when we will dope it, if it is N-type and you have added pentavalent impurity and you got the donor electron, then the energy level will be shifted, Fermi energy level will be shifted upward, and this will be the position of the Fermi energy level in N-type semiconductor. And here you added trivalent impurity. So trivalent impurity is doped in the intrinsic semiconductor, then the Fermi energy level will be shifted downward. So this will be the position of the Fermi energy level, and the concentration of hole will be more than the concentration of electrons. The Fermi energy level will be below the intrinsic Fermi energy level. So this is P-type semiconductor, P-type semiconductor.